That gives me great pleasure to introduce Bill. Actually, I was a student in Bill's first class ever at the University of Buffalo. That was his first year at Buffalo, and I was a first year graduate student with no idea of what I was, supposed to do or study. And of course, after Bill's class, I realized that as much as humanly possible, I should study everything. But I always think of Bill, at least for me, as a teacher, and what I've always sort of really admired is his generosity of spirit. I don't think I know anyone who's more generous with their time and ideas. And Bill pays the same care and attention to a question from a first-year graduate student as from a distinguished older colleague. And those are really the lessons that I've tried to learn for my own teaching. So it gives me great pleasure to introduce Bill, who's going to talk about what are the foundations of algebra and geometry.
It is an honor and a pleasure to be able to participate in this gathering. I warmly thank Susan and Keynote for organizing it, and warmly thank all of you for coming. So how shall we address this theme, 50 years of functorial semantics? Notice that, by the way, that too many authors only mentioned that one 1963 article in their bibliographies, as if I had disappeared after that. But I'm really still here, in case I have even written some papers since then. I'm hoping that comments and questions, especially from those who've been present or participated in all these 50 years, and also from everybody, will help to advance the explicit historical knowledge. I don't think a history of all this has ever been written. So that should enable us to see some paths more clearly into the future of research and education into related themes. The basic theme is the basic theme of functorial semantics, namely the application of categorical methods to the study of algebraic systems, general algebraic systems and their relationships. Indeed, still continuing after 50 years. We can certainly answer yes, because, for example, Adamek, Rositsky, and Vitale produced a textbook on the subject only a couple of years ago, and some young people are actually reading this book. There are many other examples that we can mention, recent examples. For several years in the far distant past, I had planned to write a book myself, but there was an open question of a basic nature which I thought should be solved before the book was written. But moreover, there was the development, together with Miles Tierney, of the theory of elementary toposes, the elementary theory of toposes, to put it correctly. And that led me to decide that I should devote myself much more to the various aspects of topos theory that were emerging. So I basically put the book project on the back burner under the title, Some Algebraic Problems in Functorial Semantics and Algebraic Theories. I bundled some of my notes for the book together with my thesis, when the possibility emerged for a TAC reprint. I trusted that both the solution to that general question, as well as the production of a book further disseminating these ideas, would be carried out by my able colleagues who were already contributing substantially to the subject. This trust turned out to be well justified. Let me recall what that general question was. It could be succinctly described as finding a presentation of the dual doctrine to the doctrine of finite products. Here I use the term doctrine due to John Beck, which in general was supposed to signify something like a theory, but higher. Now, there are many interpretations to this higher, so maybe even unfortunately, I use the word doctrine in quite different ways. One interpretation of higher, as I've mentioned already today, was to treat the logic of A, higher types, but B, not simply in terms of predicates on these types, but rather a mathematical model of actual proofs as opposed to mere existence of proofs. These two features were incorporated in my 1968 notion of hyperdoctrine, which has figured in some later work, for example, in Bart Jacobs' thesis, 1990, on comprehension categories, and some others. However, in the present connection, I'm referring to doctrines in the general sense of a kind of theory whose models can in turn be construed as theories. And much more specifically, again, that could still be interpreted in some very general way, but very specifically to two monads on the category of categories. Two monads on the category of categories with the property that the category S of small sets is an algebra. Categories, small sets is a definite point in the category of categories, which is Cartesian closed and carries a lot of two monad means, of course, enriched with respect to that, et cetera, et cetera. So these are referred to as equational doctrines in the Springer Lecture Notes 80 from 1969. So in particular, there is the doctrine D, whose algebras are categories with finite products. And this is, of course, the basic example of the setting for the theories of many-sorted theories of general algebraic systems in the traditional sense. Because of the two-dimensional versions of enrichment, commutativity, etc., we can rather freely make use in the category of categories of the Hom tensor formalism on bimodules coming from Cartan Eilenberg, 1956. For example, the dual doctrine of any equational doctrine is defined as the new doctrine whose value in any category C is. So D star C equals Hom D of S to the power C on the S. Remember, S is a definite object. C is an arbitrary category. It might be a lot bigger than C, in which case, who knows how much this will last. Doesn't matter. It makes sense because, more specifically, this is the dual doctrine in what sense? Because if we look at how do we call it? Let's say the category of algebras for any given doctrine D. So this is over cat and so on. Since I said, to simplify the discussion, I said that the S is always a D algebra. So, and therefore S to the C for any C is also a D algebra. So I can define the algebraic categories, the analog of algebraic categories, by taking Hom sub D of blank S. If you think of these as algebraic theories, then this is the corresponding algebraic category of its valued models, and this is a category. This is off, of course. But now here we could, since we're talking in the language of monads and so forth, we can use the John Beck yoga, which was to say that the algebraic structure of, from the monad point of view, is simply composing the two things. So D star is the monad that results down here when we compose the two things. And therefore, by general yoga we have a lifting, capital Phi, into cat D star. So the D star algebras, in other words, values of this functor always have the structure, not just of being a category, but actually being a D star category, as is evidenced by the functor Phi, which lifts that. This functor here, of course, is just next to the power blank, indicated there. And so you see that the idea, one put the question of recovering the algebraic theory from the category of algebras. Well, and there are many theorems to that effect. However, the goal of life is not always this recovery. In other words, there's much more generally one is interested not in perfect invariance, but in partial invariance. Like algebraic topology is all about partial invariance going on. So the only finding some kind of equivalence here is not the only goal. However, the doctrine of doctrines here is saying that if we hope to characterize this opposite, or these things, by some straightforward way instead of reverse way, this is the best possible approximation with respect to the meta-doctrine of doctrines. There might be stronger logics that would be needed, but this comes much, much closer. So you see, this is actually descent. The descent problem is usually posed in some very particular sense that makes sense in a particular context, but really the descent problem, again as John Beck understood it, was that if the problem is to invert some process, like say this, we want to invert this process. Well, the first thing is to note, well, what kind of values do we automatically get, inevitably, because of things arising by that process? And we should start, if we're going to try to calculate some kind of inverse, we should at least start with an object which has at least that structure. And we still might not succeed, but that's the best thing to do. So, again, in this particular context where we're dealing with adjoints, with monads and so forth, there is a best approximation to descent, which actually is another Hom, namely, take the Hom sub D star of any category A, which you hope is an algebraic category because it has all the structure of an algebraic category, and Hom that once again into sets. Yeah. So this is all very formal and correct. No size problems, nothing. These be Homs, and you can apply this in linear algebra as well. You look at D modules. Dual category is really about D star modules, not just D modules again, and so forth. And the attempted inverse, the descent constant, given by that formula. Now, the way that the actual theorems of recovery came about was to say that, well, it's not the whole. This is not this whole category, but the part of it which has some certain further properties, which can be stated in terms of that structure, but in some other kind of logic, existence of infinite products, or no, that's okay. Anyway, I can't remember what it was, but there's some additional logical conditions applied to these star structures. So this is in other words, this is the algebraic structure of all the categories of all the D algebraic categories A, as A ranges over the D. So this standard lifting, Phi, describes the maximum structure that all maximum doctrinal structure that all algebraic categories have, insofar as that structure is described by the meta-doctrine of equational doctrines. So, more specifically, an algebraic category is always more than a mere category because of the way that it arises, and indeed it is a D star algebra. So if we wish to represent or approximate some given category by algebraic categories, first step would be to verify that it is a D-star algebra. This may not be sufficient because we might need further restrictions on this descent process. But it's again very useful that we have, so in other words, to verify something, right? We have the composite here again. So the hope, the hope was that the monad here would be the identity, or that at least it would be idempotent, et cetera, et cetera. So that would be something much smaller than D star itself. So that's the measure of how well we can approximate this thing by means of descent. Okay. Now, as you can plainly see, it's written on the blackboard, D star is a totally definite thing. However, as with algebra on the lower level, totally definite things can be sometimes studied better if we have presentations. So are there ingredients and relations among the ingredients for which we could present the D star? Well, some obvious ingredients right off, right? Should have said, of course, that the naturality is extremely important. The structure that the values have means that structure which is functorial with respect to all the maps back here. This is, as underlined in my abstract, the crucial thing in some sense is the naturality. But it's clear that the change of algebraic theory as applied to the categories of algebras is going to preserve arbitrary small limits. Again, they often have left adjoints, but some side conditions may be necessary to see if they have left adjoints. But certainly they preserve limits. They preserve small limits, and because of the finitary nature of D, the doctrine D, they preserve filtered colimits, and they preserve reflexive coequalizers as well, thanks to an old paper of Fred Linton, which pointed out the crucial role of reflexive coequalizers among total algebras as opposed to partial algebras, for example. There is no special role for reflexive coequalizers in Gabriel-Ulmer semantics, but there is in the study of total operations. So now, does this constitute a presentation? Well, no, because you have to have also the relations. So between the filtered colimits and the small limits and the reflexive coequalizers, there are various distributivity and commutativity relations. So now this, what I've just described, made precise, of course, with the help of Marmolejo and other people, is a presentation of something, of some doctrine. Is it D star? Well, D star is closely related to it, but well, the precise answer is in the book of Adamek, Brzezinski, and Vitale. So I posed this question at the end of my paper on equation, so-called equational doctrine, yeah. And so Fred's remark slowly seeped in, and years later, Pedicchio and Wood more or less proved the desired result, and now the results are described in detail in the book of Adamek, Brzezinski, and Vitale. Of course, you will have noticed here that because the functor whose monadic structure is being extracted is itself a Hahn functor, that actually the monad that we want to compare with the identity is a double dualization. So I think it's very striking the analogy, the formal analogy with functional analysis But of course here, instead of real numbers, the basic quantities are small abstract sets. So what is this notion of algebraic structure? It seems to, first of all, it refutes the idea that an algebraic theory is just syntax somehow, a very common mistake. Syntax can be used to present theories, and that's one role for them, but they also arise as structure of something in a context where there is no presentation in sight. It also refutes the idea that was sometimes expressed that the algebraic theories constituted a, quote, new or alternative approach to universal algebra. This is misleading. Things that label themselves as new often fail. I didn't label it as such. These ideas constitute an essential feature that was long implicitly present, and it was just a question of bringing them out and making them explicit. For example, the study of cohomology operations, which I like to cite as a motivating example. I think people study cohomology operations a few at a time, around about 1950 or something, and then they gradually realized that, well, actually these are nothing but natural structure. These are the natural transformations between the functors and all. So that's exactly the idea of the algebraic structure as in the algebraic case, structure in the algebraic case. But then it was realized, well, this is a definite thing. What is it? Does it have a presentation? So again, the heroes of the 50s, Steenrod, Cartan, etc., and finally Adem, famous Adem relations, finally completed the project of finding a presentation for this theory, multi-sorted theory, which was already known very explicitly in one sense. So, another thing about the algebraic structure is that one could remark that, well, going back to this particular case of algebraic theories now, it's really, you could say, well, it's really just a remark that in any category of products, every object has its clone. You can look at its powers and maps between it, and that's an algebraic theory. However, it's very crucial to the content that we're talking about a functor category. So that what the maps are is very strongly constrained by precisely by nature of it. So I like to. I recently thought of a simple example. If you've heard me lecture before this year, you probably heard me mention it. But it's just to illustrate that the underlying idea is extremely basic. Suppose I have a category of, call it a population of individuals, and there's some observation that I make on these, whose values are finite sets. And suppose it's functorial. That's another big assumption. Of course, you don't really need a category for that. For the graph would be finite. So you have a population of individuals with some definite relations between them, by arrows, and some way of assigning to them sets, but in such a way that every arrow gives rise to a map. Well, so now you can say, what does this functor of u tell us about an object? Well, you can say, well, of course, we could define n of x to be the cardinality of u of x. So that there's a number attached to these objects, so there's a little bit of a label that we can attach. But actually, from this setup, we can extract much more information about this particular object, because we could say, for example, define the group G to be the automorphisms of U. Automorphisms of the functor. Notice that means, of course, natural. And again, by the basic principle of lifting of the structure, there's a functor U which goes to finite G sets. And now, you see, well, because of the known structure theorem for finite permutations and so forth, we have potentially much, much more information for distinguishing objects, because we can write this. Now this is some linear combination over all subgroups, or more precisely over the objects and classes of subgroups of some coefficients in sub h times g as g mod h. Okay. So these times the cardinality of g mod h. So these coefficients, you see, are a whole array of operations. If the two objects x and y are such that they give a different set of coefficients, then they're different. So we have a much refined way of distinguishing the objects, still using basically the functor u, except becoming conscious. It's like extracting concepts from experiments. We decided to start calling these things population and samples and so forth. And this is the long sought qualitative statistics, whatever. And of course, this is just to make it simple. When we talk about a group, we go to exactly the same situation. Instead of looking at only an invertible endomaps of U, we could look at all endomaps. That would give us an even richer thing. Or, you know, for example, among endomaps, there are item probes, and these help a lot to split things up. Or we could actually consider not only unary operations, but binary operations. In other words, the full algebra structure in the sort of canonical example. And all those would give still better. It's just that in the case of G actions, we have an operary. We already know how to analyze the G algebra, so to speak. So this illustrates how. Yeah, so I would. So this is okay. This is kind of conjectural. You see, in other words, it hasn't been fully worked out, but I claim that natural structure, with respect to a given doctrine, and of course that's going to be a limitation, is thus a precise mathematical model for a very general scientific process of concept formation. Observing a domain or a population of individuals that form a collective due to definite mutual relations, and recording these observations as a structure that varies in a natural way with respect to these mutual operations, leads to the emergence of general concepts that are abstracted from all the individuals, which may then be applicable to larger populations, right? And in terms of which, and as we've just seen, in terms of which a more precise analysis of the individuals themselves becomes possible. Now, so far as this discussion went, the mutual relations, I think this could be a graph. Mutual relations need not be composable, since in any case the naturality condition that they impose depends on only finitely many at a time. But notice that we could consider finite subgraphs. Each finite subgraph would give rise to its own concept, and we could then increase the size of these finite subgraphs and obtain the total structure of the whole population as the inverse limit of one that's calculated on some, each one being calculated on a finite graph. That's why I said that's because the process of extracting structure, at least in the canonical example and many others, is a left adjoint, you see, to a contigrating functor, so direct limit goes over into inverse limit. On the other hand, there, of course, more is to be gathered and more is to be gained if the mutual relations can be construed as a category. Because then there's the possibility that the basic measurement functor itself might be representable. In which case, all this is really just talking about the category of representing objects. So that's how the cohomology operation problem was solved, quote unquote. He said, oh, it's just a category of algebraic plane spaces, basically. Which is still not a complete presentation, but it's much closer. So this is sort of like, no, I was going to say, it says that the concept of the whole population reduces to the concept of the 1%. Sorry, bad joke. Couldn't resist. Actually, I like bad jokes. Okay. No, so as I said, as here, the lifted phi, often has a left adjoint, and which can be considered the best attempt at descent. Again, even if it's not an actual inverse, the descent problem is still interesting. And here, in the case of this descent story, it's again given by a Hom, so that the resulting monad here is a double dualization with this accompanying Dirac map and so forth. Now, I wanted to say that to advocate, be my own devil's advocate or something like that. No. That the deeper categorical study of syntax itself has been rather neglected. Why? Because, well, there are two oversimplified views. One view is that only syntax matters, so that, of course, prevents one from studying it in its proper relationship. Or there is the new revolutionary claim that syntax doesn't matter at all, which once again, I never said, even as some of my would-be friends have. Well, they are friends, but they're just trying too hard. Okay. Because, you know, well, that was the basic thing that everybody knows is that not only is the syntactical presentation of a theory not unique, but even the style of what is meant by a presentation is subject to some choice. For example, the usual choice, again, coming back to single-sorted algebraic theories, there's the theories which are, of course, contained in the Pat D. The single-sorted ones, we have simply an underlying signature, calling sequences of sets or signatures. Right? And what it does is just assigns to every theory this, I understand the standard notation for objects, A to the N and A, right? So that's the nth set in the signature, the total signature of the theory, the set of all expressible algebraic operations of the theory T. Now this has a left adjoint, which of course assigns to every signature the free algebraic theory, whose own signature, of course, is much larger. Now, the point about the syntax is that, like many adjoint pairs, or even maybe all, like many adjoint pairs, this one can be factored into two stages. And here lies the category, the syntax, or the category of presentations. Again, having no necessary relation to semantics, syntax is not adjoint to semantics. If anything, it's adjoint to this, right? But the point is that even this is not unique. There's some choices, you see, because I suppose if you call, let's call this U and F, instead of getting out of letters. The most obvious notion of a presentation is a pair of maps from one signature S into the underlying, the free of some other signature S. Well, let's call this one R for relations, and this one G for generators. Okay, so, and then if you do this, then it's natural to think of this as the left-hand side of an equation and the right-hand side. Because the idea that each element of R is serving as the name of an equation. What is that equation? Well, it's the one whose left-hand side is given by this and right-hand side is given by that. But of course, they are usually not in G, but in the free thin generator. And then whatever the style that you choose, the last part is just taking a co-equalizer in T. That's what you mean by the process of presentation. I'm spelling it out because it's not often said explicitly. So you see, by the very adjoint, this is going to give rise to some map in the upper category, which in this case is theories. It's clear that exactly the same story applies to algebras of any fixed sort. Applying it to theory. So we get two homomorphisms upstairs from f of R into f of G. And so the process of presentation is to take the co-equalizer of that. So this is one basic story of syntax. Now, there are some variations on this which may be useful. One is that we can exploit the fact that, after all, we found out that the dual doctrine has co-equalizers in it, reflexive co-equalizers in it. And so maybe it would be good to arrange that every presentation contains in it a proof of x equals x for every x. You see, that would be saying, that would mean that in other words, it's just an additional, at least each generator, you see, would be a particular relation, which that for each generator, this is the name of a proof of the standard proof that G equals G. There may be other proofs that G equals G. So the reflexivity would fit very usefully with the fact that the underlying sets preserve reflexive co-equalizers in these kind of categories. Another variation on the how to factor this would express the following idea, which somebody told me long ago is very important for computers, but then nobody's been able to tell me since why that's true. And it's the following, that every equation that you actually name could be of the form that some complicated word, another element here, is to be identified with just some particular letter, a variable or a generator. Now, clearly you can present anything you want that way, because if you want one expression to equal another expression, you could just say, well, let's invent another letter, and let's set them both equal to that, and then as a consequence of well-known rules of logic, they will be equal. And again, I think probably there are objective mathematical facts that explain why that's more virtuous than the other way, but I don't know exactly what they are. Of course, that could be combined with, it would be somehow relevant to combine that with this idea of incorporated reflexivity also. So in other words, in short here, these 3 or 4 remarks are just a suggestion that, well, neither do we love syntax at the expense of everything else, nor do we throw it away. We should actually clarify some issues involving the syntax in this style or related ways. Does anybody know why that's important? Every equation is of the form an expression equals a variable. Okay.
Not exactly that, but it seems to me Heidelberg at one point, maybe in work with LDOT, maybe in work with somebody else, spent a lot of time on relations in which the left-hand side was more complicated than the right-hand side.
Yes.
It wasn't that the right-hand side was so simple as to be a generator, but when you had a numerical measure of complicatedness, and it strictly decreased, It made some sort of programming much easier. I don't know. I don't remember more than that.
No, that's one of the people who thought about that clearly. Yes, you're right. You're right.
For inductive purposes.
Inductive purposes, yeah. Now, I want to mention once again an old conjecture of William Boone. I think I've mentioned it again many times. William Boone was a specialist in group presentations, word problems as they're called, in Illinois, and I met him several times at math meetings, and he would always run up to me and say, "It should be true, it should be true." Okay. Well, he died, and I don't know if he ever proved it or not, but the idea was that we should get together sometime and prove it, but it's going to be difficult. But the conjecture is this: it has to do with presentations. It's an analogy. Boone, his name is Boone. It's an analogy with two known results in two different categories. Namely, there's a result of Graham-Higman for the category of groups. And there's a result of two logicians, Craig and Vaught, which holds for the category of first-order theories, which of course is in many ways a much more complicated category, but they proved the thing there too. And what is the thing? The thing is that if something is presumed to be finitely generated, that is, G is in some sense finite, but if now in terms of that, one can, for a suitable T, suitable doctrine or whatever, one can concoct an idea of recursivity and for the words, and so one could require that this R be a recursive set, okay, recursive set in some sense. And so then you have what's called a recursively presented group, the group that results from that by taking the co-equalizer. And the theorem is that recursively presented, meaning that R is recursive, G is presumed finite, is the same thing as being embeddable into finitely presentable. So in other words, you can enlarge the number of generators, still finite, and there you can find a finite set, R prime, both of these are finite now, which presents the same thing. So that what you go up with, you take the co-equalizer is equivalent to the same with the original. So that's a famous theorem in group theory. And maybe it's not so well known. I think it's very amusing. It was a long time ago. I knew Craig and Vaught in Berkeley. They had already proved it long before that. They get a first-order theory that has finitely many undefined predicates and recursive set of axioms. There's actually a sub-theory of another one that has a few more predicates, but only a finite number of axioms, which will then generate all of the trace on the given thing. Of course, there's a well-known example of that, namely Zermelo-Fraenkel set theory is embeddable in Gödel-Bernays set theory, and the latter is finitely related, finite number of axioms. So anyway, Boone's conjecture is that the same result is true for the category of algebraic theories in, well, let's say, first in my narrow sense. Now this is, see, in my naive vision, the first order theory case is sort of obvious. Well, it's not obvious, it's very complicated, but the point is that with first order theories you can do things like you can adjoin some new predicates, a new finite number of axioms, which is kind of a partial description of natural numbers and words and all that stuff. You see, having done that, you can then encode your original theory into that and write down one more axiom which says all the axioms are true.
Yes.
Right? So that's the typical thing that you can do, but it's using the expressive power of first order theories. Now I don't actually know how Huygens proof works. Maybe somebody here does, but you see, there's no clear way that you could do something like that with just equations only. So, but I hope somebody will find this theory. The noble goal of general theory is to illuminate the path of further structures, further struggles, both practical and theoretical struggles. That goal is often obscured by the allure and the attraction of a new or more universal theory, deviating us from carrying out the path of actual applications. So we are especially happy to have seen today several cases where universal concepts can again be particularized in such a way to illuminate the further development of, for example, commutative algebra itself. How much time do I have? 14 minutes. 14 minutes, good. Now, of course, the title was Bill Lawvere and 50 years. We wouldn't talk about Bill Lawvere. I would say, right now, I'm very interested in cohesive toposes and classifying cohesive toposes according to their role in topology and analysis and so forth. But because the main title was algebraic theories, I won't say anything more about that. So leaving 13 minutes now, I hope that my initial plea at the very beginning, namely that there'll be comments and questions about this 50 years or about the last 50 minutes, which we can use to help make it more explicit our picture of the whole thing. Counted on for the first question.
I have a strong memory, haven't thought about it